Imagine a place where every 60 seconds, a brand new car rolls off the line, perfectly assembled, ready to drive. Not in Japan, not in America, but deep in Rajasthan, India. This is Honda's Tapukara plant, the largest integrated Honda factory in the world. And what's happening inside this massive complex isn't just impressive, it's rewriting the rules of modern manufacturing. From the outside, it looks like any other industrial site. But inside, it's a world where robots don't sleep, machines don't wait, and every second is calculated. Massive 4,500-ton press lines forge crankshafts in under 9 seconds. Automated guided vehicles glide silently across polished floors, delivering parts with zero human input. And an army of precision welders and AI-driven arms build cars faster than any plant Honda has ever created. This isn't a factory, it's a symphony of steel, sensors and software, a place where technology and discipline merge to create one of the most efficient production lines on Earth. And while the spotlight often shines on Tesla's flashy moves, Honda has quietly built a monster, a machine so fast, so scalable, that it delivers a fully built vehicle every single minute. This is not just about speed, it's about a global shift in who controls the future of mobility. And Honda? It's no longer just playing catch-up, it's playing a different game entirely. If this blew your mind, hit like, subscribe, and join us as we uncover the future, one factory at a time. Across 4 continents, Honda has built a manufacturing system that runs with near-surgical precision. But the average consumer has no idea what's happening inside these plants. At the core of it is a factory network designed not for headlines but for output, scale and speed. The Tapukara plant in India spans over 450 acres, making it Honda's largest integrated facility in the world. It handles everything from engine assembly to frame manufacturing, pressing, welding, painting, casting and vehicle final assembly, all in one location. This allows Honda to compress lead times and logistics costs drastically. It also means the plant doesn't just assemble cars, it manufactures them from raw materials up. Tapukara isn't an outlier. It's part of a global strategy that includes the Marysville auto plant in Ohio, which opened in 1982. It was the first Japanese car factory built in the United States. Now, it's a key component in Honda's EV transition, recently announced to become the company's first North American EV hub. Nearby, the East Liberty Auto Plant and Anna Engine Plant round out the Ohio production network. Combined, Marysville and East Liberty cover over 8 million square feet of manufacturing floor space. Anna alone has produced over 30 million internal combustion engines, a number that puts it among the most productive engine plants in North America. These aren't inflated figures, these are live operational metrics. In terms of output, Tapukara has a capacity of up to 1.8 million vehicles and two-wheelers per year. That's roughly one vehicle produced every 60 seconds when running at full capacity. This isn't theoretical. That rate is sustained across peak quarters and is documented in annual production reports submitted by Honda India. But the defining feature of these plants isn't their size, it's the manufacturing density and automation. Inside Marysville's paint shop, there are 84 industrial robots handling all priming, coating, and finishing operations. Each robot is calibrated to handle specific components with minimal overspray, optimizing both material usage and environmental emissions. The result is a system that maintains uniform paint quality while reducing operational waste. At Tapukara, Honda deploys a 4,500-ton forging press, one of the largest in Asia. This machine produces a crankshaft every 9 seconds. Most factories require several stages to produce engine components like these. Here, it's a single-stroke, high-tonnage operation that eliminates intermediate handling, improving throughput, and reducing potential points of failure. Welding operations across Honda's global plants are also heavily automated. In Marysville, the underbody weld line operates with minimal human intervention. Robotic arms equipped with servo welders perform real-time feedback adjustments during each weld. Tapukara follows a similar configuration. These systems not only increase precision, but also reduce quality inspection rework by up to 35%. In terms of automation scale, Honda operates with approximately 70% automation in its newer or updated plants. That percentage includes welding, painting, and major material movement. Older facilities are progressively being retrofitted to match this standard. Internal transport inside these plants relies on AGVS, automated guided vehicles, to move parts between departments. These units are fully autonomous, equipped with LiDAR and magnetic floor guidance. In Tapukara, AGVs deliver components across 3 assembly zones and 5 sub-assembly areas without requiring operator input. Honda's GAC plant in China pushes this even further, integrating AGVs across the entire stamping to final assembly pipeline. These automation systems are monitored by a centralized control center. Each AGV, welding robot, and press machine is connected to Honda's internal production control software, which tracks cycle time, output rate, error codes, and predictive maintenance flags. In Marysville, this is handled by a customized version of DeviceWise, a middleware platform that connects legacy equipment to modern IIoT protocols. The data generated isn't just for live monitoring. Honda uses real-time analytics to optimize staffing, reroute parts, and prevent downtime. According to internal reports, the predictive maintenance algorithms deployed in Ohio have cut unplanned equipment downtime by 23% over the last 3 fiscal years. This system-level integration allows Honda to operate with low buffer inventory, reduce takt time across assembly lines, and maintain operational uptime that exceeds 95% across its global facilities. For context, industry average uptime in legacy plants often falls between 85 to 90%. And while much of this automation replaces repetitive labor, Honda still relies on human operators for critical tolerance checks, high complexity installations, and line supervision. The workflow has shifted. Humans now manage and troubleshoot systems, while robots execute the majority of the process-driven tasks. What's most notable is that none of this is recent. This isn't Honda racing to catch up. These systems have been in operation and expanding incrementally for over a decade. The scale, the density of automation, and the volume of vehicles produced have all been deliberately constructed, not as marketing assets, but as operational advantages. When combined, this manufacturing footprint represents one of the most refined vehicle production networks in the world. Not the loudest, not the flashiest, but among the most productive, scalable, and digitally integrated. Inside Honda's production system, the line between human and machine isn't being erased, it's being redefined. Honda has integrated collaborative robots, cobots, directly into its frame assembly lines across major factories in Japan and India. These cobots handle precision installation, welding, fastening, and real-time tolerance adjustments. Unlike traditional robotic arms programmed for repetitive, isolated functions, cobots operate alongside human technicians in shared work zones. They are equipped with advanced force sensors and adaptive software that allows them to slow down or halt immediately upon detecting human proximity, maintaining both safety and speed. In Tapukara, cobots are used to install fuel lines, perform joint sealing, and apply adhesives at a consistency that surpasses manual labor. In Japan, at the Yoriai plant, cobots have reduced human error in chassis alignment by over 40%, while improving takt time per station by 18%. Across both locations, their deployment has reduced repetitive strain injuries and decreased production line fatigue among human workers without sacrificing cycle efficiency. While robots execute mechanical tasks, artificial intelligence runs the decision-making layer in the background. Honda's manufacturing control systems are integrated with predictive AI algorithms that track every machine's operational behavior. In Marysville, over 3,000 machines feed live telemetry into centralized systems that flag anomalies before they become failures. Internal data shows that these predictive models are now identifying over 95% of potential maintenance issues up to 48 hours in advance. This lead time allows maintenance teams to schedule interventions during planned downtimes, eliminating disruptions. In Honda's powertrain assembly lines, AI doesn't just monitor temperature, pressure, or vibration, it compares that data against historical baselines and instantly triggers escalation protocols when outliers are detected. Operators no longer wait for failure signals. They receive alerts before degradation even begins. This predictive layer has enabled Honda to maintain an average machine uptime above 96% across high-volume plants over the last 5 years. In environments producing hundreds of vehicles per day, that level of consistency directly translates to higher throughput and fewer production bottlenecks. Parallel to robotic integration is a factory-wide transformation in how materials move. Honda has phased out manual part movement in favor of automated guided vehicles, AGVs. These units are now deployed across all major vehicle and powertrain assembly plants, replacing forklifts, carts, and low-speed manned tuggers. In the Tapakara plant, AGVs connect press shops, welding zones, paint shops, and final assembly lines through predefined magnetic tracks and onboard sensors. These machines transport engine components, suspension units, and doors across the facility without needing human input. Each AGV is monitored via centralized fleet management software, which tracks traffic density, schedules dispatch routes, and maintains collision avoidance across intersections and high-traffic merge zones. In Honda's GAC facility in China, AGVs don't just follow lines, they manage live intersection logic using LiDAR and RFID. When two AGVs approach a shared path, one dynamically yields based on delivery priority and battery status. Traffic control decisions that once required floor managers are now handled autonomously. This automation reduces lead time between operations, eliminates idle parts, and increases material availability accuracy. In Jiaxi, AGVs have helped reduce line starvation incidents by over 70%. They've also enabled uninterrupted production in overnight shifts, where human logistics staffing was previously a limiting factor. Honda's internal reports estimate that AGVs have cut intra-factory logistics labor requirements by over 60%, while simultaneously increasing reliability. But this level of precision in flow and logistics only matters if the production lines are as agile as the supply chain. That's where Honda's modular production design gives it a major edge. While most legacy OEMs maintain separate lines for combustion and electric models, Honda has taken a different approach. In its Alliston, Canada facility, the same production line has been retooled to manufacture both the CR-V hybrid and traditional gasoline variants. There's no duplication of infrastructure, only shared hardware, adaptive fixtures, and software-driven reprogramming. This transition was completed without stopping production. Engineers integrated additional robotic units for battery pack installation and modified inspection checkpoints for hybrid-specific systems. Changeover between ICE and hybrid variants on the line occurs without mechanical intervention. The system detects the incoming model variant using VIN-linked production codes and adjusts torque settings, toolpaths, and part feeds in real time. At the process level, Honda's multi-powertrain lines are 100% modular. Fixtures are universal, robots are flexible, and line logic is controlled by software that receives model-specific data at the start of each build sequence. That modularity is critical to Honda's electrification roadmap, where volume shifts between ICE, hybrid, and EV units are expected to fluctuate over the next 5 to 10 years. Rather than building entirely new lines, Honda can scale up or down hybrid or electric production volumes on existing lines by updating digital instructions and reassigning material flow priorities. This system is already active in multiple locations. In Japan, the Yori plant uses a similar layout to produce compact electric hatchbacks alongside conventional models. In Ohio, retooling is underway to align with Honda's EV hub strategy. The company's upcoming e-architecture vehicles and those developed under its Ultium partnership with GM are being planned for integration into shared lines using this same methodology. That's a strategic difference. While competitors must pause and retool, Honda's infrastructure is designed to adapt while running. This integration also eliminates redundancy. Shared tooling, universal jigs, and platform-based modularity reduce part handling errors, minimize tooling inventory, and simplify maintenance. The result is faster line balancing, lower per unit costs, and real-time responsiveness to market demand. This operational structure isn't theoretical, it's active, measurable, and expanding. Honda's production system is no longer segmented by powertrain. It's been engineered to operate as one unified, intelligent, flexible ecosystem. Inside Honda's production network, silence isn't a side effect, it's a feature engineered directly into the system. In both the Tapukara plant in India and the Marysville facility in Ohio, high decibel operations like forging, welding, and body joining have been redefined. Instead of using traditional friction welders or hammer presses, Honda employs ultra-quiet servo-driven welders and laser brazing systems to reduce interior noise to below 75 decibels, which is equivalent to the ambient sound level in a library. That's not for comfort, it's to maintain a controlled acoustic environment where every anomaly in machine noise can be detected and flagged in real time. This quiet process is built into critical operations like roof joining and frame panel sealing. The laser brazing system, used at Marysville, eliminates mechanical impact during roof-to-body integration, creating a clean, seamless joint while generating far less noise and vibration than traditional spot welding. It also requires less post-process finishing, which saves additional cycle time. Servo welders in Tapukara operate with programmable pressure levels and minimal physical noise, enabling continuous real-time monitoring without acoustic interference. This level of acoustic control isn't isolated. It integrates directly into Honda's expanding electric vehicle production roadmap, specifically the company's next-gen EV platform, referred to as e-architecture. This system is being developed to compete directly with Tesla's 4680 battery structure, offering high energy density with improved integration into the vehicle chassis. Honda's e-architecture is being backed by a major infrastructure investment, a $4.4 billion joint battery plant in partnership with LG Energy Solution, currently under construction in Fayette County, Ohio. The facility will produce lithium-ion battery modules optimized for faster charge cycles and thermal stability. According to the latest manufacturing disclosures, these new battery packs will be capable of reaching 0 to 80% state of charge in under 25 minutes, matching or surpassing current industry leaders in charge speed. Unlike legacy systems that bolt battery packs underneath chassis frames, the e-architecture design integrates the battery modules directly into the vehicle structure. This improves weight distribution, increases structural rigidity, and simplifies thermal management. The design reduces the number of components required by up to 20%, cuts wiring harness length by nearly 30%, and improves overall manufacturing efficiency across stamping, welding, and final assembly. These gains are essential to Honda's plan to scale EV production across North American facilities without pausing existing hybrid or combustion lines. At the core of this entire system is a digital infrastructure that allows every layer of production to be tracked, adjusted, and optimized without delay. In Honda's Ohio plants, this is accomplished through the use of a platform called DeviceWise, an industrial middleware that connects legacy machines, robotic cells, sensors, and software into one unified network. Over 200 systems, from paint line actuators to welding robots to AGV fleet controllers, are linked through DeviceWise. This allows for synchronized data capture across processes, meaning temperature spikes on a battery module line, welding misalignment on a door frame, or voltage drops on a test station are all registered simultaneously. The system flags outliers and pushes them into a central alert queue used by both engineering and maintenance teams. But this goes beyond alerts. Honda has built predictive maintenance models on top of this data layer. These models use historical behavior patterns, current operational variables, and environmental inputs to forecast potential machine failures before they happen. In the Anna engine plant, predictive maintenance has reduced unplanned downtime by over 20% annually across key engine machining and block assembly lines. These models calculate wear levels, flag high-risk components, and generate automatic part requisitions to pre-stage replacement parts during scheduled downtime windows. When failures do occur, the system reroutes operations where possible. On the final assembly line in Marysville, if one robotic arm in the underbody station flags a hydraulic fault, the system can activate a pre-calibrated backup unit without operator input. It can also adjust the takt time of upstream and downstream processes to absorb the delay while keeping total line flow continuous. These interventions occur within seconds and are logged in the production record in real time. Honda refers to this as dynamic rebalancing. It ensures that single-point failures do not stall entire lines. According to internal documentation from the Production Engineering Division, these auto-recovery protocols have helped Marysville maintain an average line efficiency of 97.6% over the last 24 months, well above the North American manufacturing average for mixed-model lines. Operators at these facilities are no longer simply executing tasks, they're supervising systems. Their dashboards include diagnostics from welding heads, sensor statuses, AGV fleet heat maps, and torque readouts from battery installation arms. Anomalies are color-coded and sorted by priority. Maintenance schedules are now driven by actual usage patterns, not calendar intervals. And as Honda rolls out more integrated EV platforms, these digital layers will scale with them. What used to require a team of specialists now runs as a closed-loop ecosystem where machines detect, respond, and adjust faster than human input allows. These aren't trial systems, they're active and expanding. Every new line added to the EV transition pipeline is being designed with this infrastructure from day one. The combined effect is a system where failure is anticipated, delays are contained, and response times are automatic. Honda's plants aren't static. They're actively analyzing themselves in real time without waiting for human intervention. And that's exactly how they plan to meet rising EV demand without adding chaos to production. Honda's factory network isn't just automated, it's engineered for resource efficiency at scale. At the Tapukara plant in Rajasthan, every drop of water that enters the system is accounted for. The facility runs on a zero liquid discharge model, meaning wastewater from cleaning, cooling, and processing never exits the plant untreated. It's collected, filtered, recycled, and reused across operations like paint shops and cooling towers. This isn't a pilot. It's fully operational and audited under India's Green Manufacturing Certification protocols. Beyond water, Tapukara has implemented rainwater harvesting systems across its rooftop and surrounding catchment areas. During peak monsoon months, the plant collects tens of thousands of kiloliters of rainwater, which is stored and fed back into the facility's greywater system. Rooftop-mounted solar panels supplement plant energy needs during daylight hours, reducing grid dependency and flattening peak hour load curves. In Marysville, Ohio, Honda's approach is similar but scaled to North American infrastructure. The site includes a 7-acre water retention pond designed to recycle runoff water used for process cooling. This closed-loop system feeds chilled water through manufacturing lines, eliminating the need for large-scale municipal water withdrawals. The thermal exchange is monitored in real time, allowing technicians to maintain optimal temperature without excess energy waste. The company's Chinese EV production hub, operated through GAC Honda, includes a 22-megawatt solar installation, one of the largest of its kind for a single automotive facility in the region. The output offsets approximately 13,000 tons of CO2 annually, based on grid power replacement metrics verified by regional energy regulators. This isn't green branding. It's integrated into the plant's operating model with load balancing software that prioritizes solar draw before tapping into external supply. While these environmental systems are evolving, Honda's output on the two-wheeler side has already reached global dominance. India remains the operational epicenter. Honda Motorcycle and Scooter India, HMSI, operates 4 major facilities: Manesar, Haryana, Tapukara, Rajasthan, Narsapura, Karnataka, and Vithalapur, Gujarat. Together they produce over 6 million scooters and motorcycles per year, making India the largest two-wheeler export base in Honda's global portfolio. These plants aren't legacy operations. They run parallel in design and tech to Honda's car manufacturing sites. Fully automated press lines form vehicle frames from raw sheet metal using servo-driven stamping equipment. Robotic welders assemble subframes with multi-axis arms that maintain dimensional tolerances within 0.3 millimeters. In the painting phase, closed-loop booths equipped with electrostatic sprayers and air recycling units ensure consistent finish quality while reducing VOC emissions. Assembly lines operate with AGV-fed logistics and programmable torque tools, just like their four-wheeled counterparts. Over 40 countries now receive two-wheelers exported from these Indian plants. Latin America, Africa, and Southeast Asia are major recipients, with India-built models often undercutting local manufacturing costs while exceeding compliance standards. These aren't side businesses, they represent a scalable platform that supports Honda's market penetration in developing regions with lower EV infrastructure. But the company's strategy isn't just to dominate conventional vehicle segments, its EV deployment timeline is already live. The first e-architecture-based EVs are scheduled to roll off the line at the Marysville Auto Plant in 2026. This isn't speculative. Construction is underway to convert existing lines, reconfigure robotic welders for new chassis designs, and adapt battery module install points into the line sequence. The plant has already halted production of the Accord Hybrid at its current site to make room for the new EV build sequence. By 2027, Honda plans to bring this EV capability to additional plants across Japan and North America. The target is to fully electrify the company's global lineup between 2027 and 2030, which includes all passenger vehicles and a substantial portion of the two-wheeler segment, beginning with urban commuter EV scooters. A key part of this rollout is Honda's collaboration with General Motors. Under the terms of their joint venture, Honda will produce a range of Ultium platform-based EVs for both the North American and global markets. These vehicles will use GM's battery and drive unit technology, while the vehicle software, interface, and driving dynamics will be handled by Honda. The partnership allows Honda to skip several years of battery R&D and move straight into volume production with a tested cell platform. But Honda is also working in parallel on its own in-house platforms. While the GM-based EVs target the mid-size and crossover segments, the e-architecture platform will cover compact and subcompact vehicles across North America, Japan, and Europe. It is being designed for modularity with shared components between sedan, SUV, and hatchback configurations. This reduces supply chain complexity and accelerates plant integration. The battery packs for these vehicles will come from the Honda LG Energy Solution battery plant in Ohio, which is expected to begin production by 2025. This facility will manufacture lithium-ion modules capable of supporting charging speeds of up to 350 kilowatts, with integrated thermal management and DC fast charging compatibility across the board. Honda plans to ship these packs not only to US assembly lines, but also to export partners in Canada and Mexico. This EV shift isn't being executed in a separate vertical. It's being embedded directly into Honda's active production flow. The same lines that currently assemble CR-Vs and Accords are being reconfigured to allow alternate runs of electric vehicles. Honda's line software has already been updated to include EV-specific inspection logic, battery module alignment procedures, and high-voltage safety checks. All of this is designed to scale without adding downtime. The EV rollout doesn't pause existing production, it expands within it. Honda's engineering teams have mapped conversion paths for every plant affected, and the same playbook used in Alliston and Marysville will be replicated across Yorai, Sayama, and Suzuka. This is not a test phase, it's already happening. Honda's long-term manufacturing strategy is increasingly centered on robotics and edge AI, and it's already moving beyond typical automation. In Japan, the company's robotics labs, best known for the Asimo project, are now focused on developing next-generation humanoid and industrial robots designed specifically for factory deployment. These robots are being tested for complex tasks such as part picking, bin sorting, and repetitive high-precision movements traditionally handled by trained operators. Parallel to this, Honda has deployed vision-based assembly systems across multiple production lines, integrating advanced cameras, depth sensors, and real-time analytics to assist robots in making micro-adjustments. These systems have already reduced human error rates by 94% in panel alignment and joint placement operations. Instead of relying on fixed motion paths, robotic arms are now dynamically adjusting in real time based on exact part orientation and environmental feedback. These systems are especially useful in final assembly, where tolerances are tight and manual correction is costly. What's changing is not just hardware, but the software logic that governs factory behavior. Honda's manufacturing execution systems are shifting towards semi-autonomous line logic. This means lines can self-adjust takt time, reroute production, or compensate for line station disruptions without central manual overrides. In testing environments, these systems have successfully rebalanced entire work cells in under 90 seconds after tool failure, a task that previously required 15 to 20 minutes of operator intervention. As these systems scale, Honda's role is no longer just that of a vehicle manufacturer. It has become a vertically integrated builder of systems, producing not just EVs and engines, but the industrial tools, robotics, software, and energy infrastructure needed to support them. Honda isn't marketing these technologies externally, but the internal deployment is expanding across both Japanese and North American plants. This transformation positions Honda well beyond traditional car making. While competitors focus on scaling vehicle platforms, Honda is embedding automation, battery systems, EV architecture, and robotics into a unified ecosystem. Every step, from module assembly to powertrain integration to logistics, is being redesigned to operate without human dependence. The shift is not temporary or reactive, it is foundational. And while much of the industry focuses on brand perception and consumer-facing features, Honda is building infrastructure at the factory level designed to function regardless of external labor variables or supply chain volatility. The company's production strategy is now structured around high-mix, high-flexibility manufacturing powered by closed-loop automation. This is no longer a legacy automaker adapting to change. It is a manufacturer optimizing for total independence across process, technology, and execution.